Okay, so in the last section of Chapter 5, in Section 5.1, we talked a little bit about sampling distributions and about biased estimators, unbiased estimators, and just a general idea of what the difference was between a sampling distribution, distribution of a sample, and distribution of a population. In this specific section, we are going to specifically talk about sample proportions and the sample. All right, so after this section, you should be able to find the mean and standard deviation for the sampling distribution of a sample proportion. Okay, and we're going to go over specifically what a sampling distribution of a sample proportion looks like. Determine whether or not it's appropriate to use the normal approximation to calculate probabilities involving the sample proportion. Okay. And finally, we're going to calculate probabilities involving the sample proportion from the sampling distribution. So some of this section will actually end up being a little bit of review after we have determined whether or not we can use the normal approximation in order to make some calculations involving the sampling distribution. Finally, you're going to evaluate a claim about a population proportion using the sampling distribution of a sample proportion. Okay, so in this section, we're going to take a look at how good is the statistic p hat as an estimate of a parameter proportion. So when we find our sample proportion, is it a good estimation of the population proportion? The sampling distribution of p hat. So remember that the sampling distribution of p hat, that's a whole bunch of sample proportions taken and made into a distribution. That's going to answer this question on how good our sample is at estimating the population. And then we're also going to take a look at the question, what happens if we take many samples? So what happens if we take 50 samples and find p hat? What happens if we take 500 samples and find p hat? What happens if we take 5,000 samples and find p hat? Okay, will p hat become a better estimate of our population p? A Gallup poll found that 210 out of a random sample of 501 American teens aged 13 to 17 knew a historically important date. The sample proportion of students that knew that date was p hat, because it's a sample, of 210 out of 501 is 0.42. This is the statistic that we're going to use to gain information about the population proportion. In this section, we're going to use the sampling distribution to clarify how to estimate the population from a sample. So sampling distribution means I would end up taking a whole bunch of samples of 210, finding their proportions, and then putting all of those proportions in a distribution. That is my sampling distribution of my proportions, because I've taken all of those proportions and I have put them in a distribution. Okay, and from that distribution, what am I going to want to look at? I'm going to want to look and see, is it unimodal and symmetric, which makes it normal, and then I'm also going to want to check, and I'm going to find the average of all of those proportions. So that's what we're going to be taking a look at in this section. Okay, so let's just take a look at a specific example of the sampling distribution of p hat. Let's consider the approximate sampling distribution generated by a simulation in which a simple random sample, so that's really important, that's an SRS, of Reese's Pieces are drawn from a population whose proportion of orange candies is 0.15. So I know the population proportion of orange candies in Reese's Pieces is 0.15. There are yellow, orange, and brown Reese's Pieces candies. All right, so let's take a look at the first simulation. In the first simulation, what we did was we took a sample size of 25 Reese's Pieces. All right, if you take a look, here's my Reese's Pieces, here's my big jar, took a simple random sample, and within my 25 pieces, I found the proportion, or the p hat, that were orange. If you take a look, okay, if we calculate this, the p hat of orange candies was 0.24, okay, from my sample size of 25. I did that 400 times. All right, so 400 times I took a sample of 25, found the p hat, put that p hat on my graph. Found another sample of 25, found the p hat of orange candies, put that on my graph. Let's just take a look at the distribution when I took sample sizes of 25, found the p hat, and put the p hat, or the proportion of orange candies from a sample of 25, on my graph. The mean the mean is 0.154. Well, what does that mean represent? That's the mean of all of these proportions. So what is the average proportion of orange candies? Well, the average proportion is 0.154. Let's take a look at the spread or the standard deviation. It's 0.071. All right, now what is going to happen if in my sample, when I look at the proportion of orange candies, increases to 50, okay? Because in this particular sample, 0.24, that's not really close to 0.15. So in my next sample, what I did was I took a sample of 50 Reese's peanut butter cup or Reese's Pieces. So in my sample size of 50, okay, I had a sample size of 50, found the p-hat of the proportion of orange candies, put that p-hat on my distribution. And then I did another time, and I did that 400 times, the same as I did over here. The only difference between these two graphs is the fact that this had each of these proportions came from a sample of 25. Each of these proportions came from a sample of 50 instead of 25. All right, let's take a look at the mean and standard deviation. Well, the mean is 0.149, closer to our population. Our standard deviation is 0.048 versus over here 0.071. Well, what did we say happens to our variability or the spread of our data? Remember, your standard deviation measures the average distance away from the mean you are. The standard deviation here is much smaller. Well, why do you think it's smaller? All of these p-hats came from a sample of size 50. So I'm averaging more together. So I have a much larger sample in order to take the proportion from. So what happens as the sample size increases from 25 to 50? All right, and remember that it's the sample size 25 and then I found the proportion of 25. Sample size of 50, found the proportion of orange out of 50 and put that on here. And there are 400 of those on each of my graphs. So what do we notice about the shape, the center, and the spread? Well, we notice, let's take a look at our graph. The shape is pretty unimodal and symmetric for both of them. The mean, all right, the mean with less is further away from the population. When I took a whole bunch of samples of 50 and found the proportion, it was closer. My standard deviation was also a lot smaller, so there was less variability. So let's just take a minute and we'll get a little bit more specific with the shape, the center. Here's what we should have noticed about the center and the shape and the spread for the sampling distribution on the previous page. Number one, the shape. In some cases, the sampling distribution of p-hat can be approximated by the normal curve. So if we looked on our previous page, they were unimodal, symmetric. They both looked approximately normal. This seems to depend on both the sample size and the population proportion p, and we'll go over that in a minute. But when we actually looked at the distribution, they were both approximately normal. Okay, how about the center? The mean of the distribution, so notice says mean of p-hat. That is telling you that is the mean of the distribution. So that is the mean of that entire graph is equal to p. So the mean is equal to p. So that's telling us, if we remember when we took a look at the samples of 50, the mean of that sampling distribution was 0.149, which was really close to the population proportion of 0.15. This makes sense because the sample proportion p-hat is an unbiased estimator of p. So unbiased estimator means that the mean of that sampling distribution is close to the mean of the population. Okay? And then what about the spread? For a specific value of p, or the population, the standard deviation, sigma of p-hat, that is the standard deviation of your sampling distribution, gets smaller as n gets larger. So if you notice, when we looked at the proportion of 25 versus the proportion of orange candies in samples of 50, the standard deviation got smaller. The value of your standard deviation of your sampling distribution depends on the sample size, and it also depends on the proportion, which we'll get to later on. So notice, take a look at the Reese's Pieces that were drawn from a population whose proportion of orange candies was 0.15. The shape is approximately normal, okay? The center, the mean of this distribution which is the mean of all of these proportions. So if this proportion is 0.15, this is 0.16. If I took the mean of all those proportions, the mean of that is 0.149. So that's the symbols for that. Okay, and the standard deviation is 0.048. So that standard deviation would be your sigma of p hat. Okay, our sigma of p hat, or our standard deviation of our sampling distribution of proportions, is 0.048. And that's really important that you show that notation, because this is showing you that the standard deviation of the sampling distribution of proportions, okay, is what specific number. Okay, so later on in the year, we're going to be talking about binomial random variables. Some of you may have heard of them before. I'm just going to show you the connection between the statistic p hat and a random variable x. If you don't understand the slide, that's okay. We'll just be going over the formulas that you need to know later on in the section, but this is just sort of where the mean and the standard deviation for your sampling distribution come from, which we will be talking about later in the year when we talk about binomial random variables. So if you don't understand this slide, it's okay. So if you have talked about binomial random variables in a different class, the mean and standard deviation for a binomial random variable x, so random variable x is just going to be a proportion of successes and failures. So the mean of a binomial random variable is n, your sample size, times the proportion. The standard deviation of your random variable is going to be the sample size times p, which is your population proportion, which is basically your number of successes, times 1 minus p, which is sort of your population failures or your q value. So really, if p is 0.4, then 1 minus p. So if you have 40% successes, 1 minus p is going to be 0.6, or 60% failures. All right, we know that p hat is x over n. So it's the number of successes over the total sample size. So how many orange Reese's Pieces over how many total Reese's Pieces we have in all. Thus, if we just sort of separate this, p hat is equal to 1 over n times x. All right, so all I did was move the x over, put a 1 here, so 1 over the total sample size times your number of successes. We can use this information to find the mean and standard deviation of p hat. Okay, how can we do that? All right, so if we take a look, the mean of p hat, okay, the mean of my sampling distribution, how can I find the mean? All right, is the mean of p hat. So what is p hat? P hat is 1 over n times x. Okay, so there's your 1 over n. What is x the same thing as? It's the same thing as the mean of that, which is n times p. So I'm going to replace this x with this n times p, and I get 1 over n times p. The 1 over n and the n cancel out to get p. So this is showing us that p hat is an unbiased estimator of our population proportion. So the mean of our sampling distribution, so the mean of the sampling distribution of our proportion of orange candies is the same as the population proportion. Okay, so the mean of the sampling distribution is going to be the same as the population proportion. That's the whole point of using a sampling distribution to estimate the mean. Okay, what is the standard deviation of the sampling distribution? All right, so when I have p hat and I have sigma p hat, that is telling me that I'm looking at the sampling distribution. I took a whole bunch of samples of p hat, found their proportions, put them on a curve, and they turned out to be approximately normal. Okay, that is going to be 1 over n, because my p hat is 1 over n. All right, the standard deviation of a binomial random variable is np times 1 minus p. Number in the sample, successes, failures. So I'm going to replace, okay, the p hat with this, the np times the 1 minus p. Now just combining these formulas together, all right, this is what it ends up looking at. If you put the n underneath the square root, you'd have to square it. So you end up with np times 1 minus p over n squared. Don't worry about the math how to get there, but it's just your p, which is your proportion of successes, times your q, which is your failures, divided by n. So this is like p times q divided by n. So basically, as your sample size increases, the spread is going to decrease. Well, why does that happen? Notice n, which is your sample size, Okay, your sample size here, as this increases, it makes your denominator larger, which makes this whole fraction smaller. So that's why the standard deviation, when I took samples of 50, was smaller than when I took samples of 25. So we're going to quickly summarize the facts about the sampling distribution of p hat. All right, take a look at our sampling distribution. So remember our distribution from the AP Stats guy that was looking at the proportion of students who thought they were sexy and they knew it. So he took a sample of size 5, found how many students thought they were sexy and they knew it. Sample of size 5, how many students thought they were sexy and they knew it. Sample size 5, how many students thought they were sexy and they knew it. And they put all those values of p hat. Okay, hopefully you're getting the idea here. All the values of p hat are going in my sampling distribution. Okay. Now, I have a curve that looks approximately normal. So remember, normal curves are defined by the mean and the standard deviation. Well, what is the mean of all of these p hats? The mean of all of these p hats is going to be the mean of the population. Why is it the mean of the population? Because we said it's unbiased if the mean of the p hats is the same as the mean of the population. So when I draw this normal curve, when I label the mean right here, I'm going to label it as the mean of the proportion. I'm going to label it as the population proportion. What is the standard deviation? So remember, I'm going to go 1, 2, 3 standard deviations, -1, -2, -3 standard deviations. So the standard deviation of this sampling distribution is the square root of p, which is your population proportion, times 1 minus p, all over your sample size. So basically successes, failures, all over the sample size, take the square root. That's going to be your standard deviation. Okay. So we took all of our simple random samples of size n for p hat, placed them in a distribution, and we wanted to find the mean and standard deviation because that's how we. All right, so here's the formulas you need to know. Here's what you need to know about a sampling distribution of a sample proportion. We're choosing a simple random sample. Notice that's really important, of size n. So that's our sample from a population of size n. So big N is population with proportion p of successes. So that's our population proportion. Let p hat, or the sample proportion, be the sample proportion of successes. So how many students thought they were sexy and they knew it. The mean of the sampling distribution of p hats is the mean of p hat is equal to p. Okay, so what does that look like? Okay, so what does that look like and what exactly does that mean? Okay, so when it says the mean of the sampling distribution, so here's my sampling distribution with a whole bunch of p hats in it. Okay, what is the mean of that sampling distribution? When I write mean of p hat, that means I'm specifically looking at the averages or the means of all of these proportions. The mean of all of those proportions is going to be the same as the population proportion because I'm saying it's an unbiased estimator. The standard deviation of this sampling distribution, so the standard deviation of this specific curve that I'm talking about that is made up of a whole bunch of sample proportions, is the square root of p, which is your proportion of successes, times 1 minus p, all over your sample size, which is n. So that's your standard deviation of that specific curve. So when it says the standard deviation of the sampling distribution of p hat is this following formula. Notation is important. Notice how you have that p hat. That tells you that I'm looking at a distribution of a bunch of sample proportions. Sigma p hat tells me that this is a standard deviation from a curve that is a bunch of proportions. Now, and it says as long as the 10% condition is satisfied, so that means, remember, that your population has to be 10 times the sample size. Okay, so this is basically saying that the population has to be 10 times the sample size. Okay, what else has to be true in order to use this? All right, number one, as n increases, the sampling distribution becomes approximately normal. Before you can perform any normal calculations, which means before you can use this mean and standard deviation, you have to check the normal condition. So what is the normal condition? How do we essentially prove that it's approximately normal? I take my sample size times my population proportion, that has to be greater than 10. Then I take the sample size times the failures, and that has to be greater than 10. Okay, now I'm not going to really explain where that comes from right now, but this is sort of like a tipping point. If the successes times the proportion, so if your sample size times your successes and your sample size times your failures are both greater than 10, that's going to give us an approximately normal curve. So that's sort of the tipping point. If that's not true, then we can't necessarily say that my sampling distribution of p hat is going to be normal. So we want to make inference about a population proportion p. That inference is based off the sampling distribution of p hat. Okay. This can be done when the sample size is large enough. Okay. When I'm talking about the sample size of each p hat. Okay, so that means if I'm taking a p hat of 50 or a p hat of 100 or a p hat of 75, that's what I mean by sample size. So I'm taking a sample of 50, finding the p hat, taking a sample of 100, finding the p hats, taking a sample of 75, finding the p hat, and then, okay, if that sample size is large enough, not the fact whether there's 75 p hats or 80 p hats or whatever. It's talking about the sample size of which you're finding the p hat of. Okay, if the following conditions are met, the sampling distribution of p hat is approximately normal. So how do I know if it's normal? So these conditions and assumptions are something that we're going to be talking about a lot. So sort of get used to this wording. The first condition we have to meet is that n, your sample size, times p, or the population proportion, is greater than 10. N, your sample size, times, you'll see this often as q, as 1 minus p is also greater than or equal to 10. That proves that our sampling distribution will be approximately normal. Now, you must show the numbers plugged into the formula to verify the conditions. Then you can use your normal approximation. So you're going to have to show that 50, so if we had sample sizes of 50 from our Reese's peanut butter times 0.15, okay, what is that? Is that greater than or equal to 10? And then 50 times 0.85, which is our failures, okay, the proportion of candies that were not orange, is greater than or equal to 10. If those are both true, then the distribution is approximately normal. It's never perfectly normal, it's approximately normal. Okay, please show the numbers plugged in to the formula. Then we'll be able to use the normal approximation where the mean of the sampling distribution is the mean of the population and the standard deviation is the square root of the successes times the failures divided by the sample size. Okay, remember it's the sample size of each individual. Okay, before you use the normal approximation, you must check the following in context. Okay, so these are the conditions that you're going to have to check. So you did your sampling distribution, you have all your p hats, you have the mean, you have the standard deviation, but you can't do anything. You can always find the mean and standard deviation, but you cannot do anything with it until you verified the following conditions. Number one, you have to make sure you have an SRS. Remember, we're using this to make an inference, a conclusion about the population from a sample. So remember that a random sample allows us to make an inference about the population. Okay, number two, then you're going to check to verify that the distribution is approximately normal. No distribution is perfectly normal. Don't ever say normal. Make sure you state approximately normal, nearly normal, something. The successes times your sample size is greater than 10. Your sample size times your failures is greater than 10. Show your numbers plugged into that formula. Okay, you're going to verify the 10% condition of independence for the standard deviation, that the sample is less than 10% of the population. So you're going to say, okay, my sample size of 50 candies, okay, what's 50 times 10? 500. There's probably more than 500. There's probably more than 500 Reese's pieces out there. Why do we have to verify that 10% condition? Because we're sampling without replacement, and when we're sampling without replacement, what happens often is that actually changes that proportion, and if the sample size is large enough, then that proportion is not going to change. So the sample size always has to be smaller than less than 10 times the population. Okay, if one condition is not met, you can say, hey, we're going to still do these calculations. There's no reason you can't do the calculations, but you just want to make sure that you state, okay, so I'm doing these calculations, but we want to proceed with caution. All right, let's continue our takeaway. So if our sample is a SRS, so simple random sample of size n, then the following statements describe the sampling model for p hat, or our sample proportion. The shape's approximately normal. Okay, we've seen that a couple times, so if you got that down. The assumptions and conditions that we have to know is that the sample size is large enough and it's a simple random sample. In order for it to be approximately normal, your sample size times your successes have to be greater than 10, and your sample size times your failures have to be greater than 10. You must show the work plugged into that formula. The mean of our sampling distribution p hat is, the mean of p hat is equal to p. So the mean of that nice curve that we have is the same as the population proportion. The standard deviation of that nice curve that we drew is your successes times your failures divided by n, or your sample size. What's our assumptions? That the individuals in the sample are independent, okay? What's the condition? So the assumption is we're assuming that they're independent. How do we prove that? That the population is at least 10 times as large as the sample, okay? The mean, so what about the AP exam and the formula sheet? So the mean and standard deviation are on the AP exam formula sheet. So this right here is on your AP exam formula sheet. So what's the takeaway from that section? This formula right here. All right, takeaway. Also on the your parameter AP P sheet. Is the population proportion. In practice, okay, so what's the next step in this process? So we stated what we're doing, we planned, we did our assumptions and conditions, now we're gonna do. Okay, so we're actually gonna figure out the calculations. So what is the probability that the random sample of 1,500 students will give a result within 2 percentage points? All right, we're actually back to normal calculations that we've done in the past. All right, so if we draw this nice normal curve, it's a curve of a sampling distributions of 1,500 students. If I draw a mean down the middle, what is the mean of that sampling distribution? The mean of that sampling distribution is 0.35. Remember, the mean of the sampling distribution is the same as the mean of the population. Okay, so you want to make sure you write that. Mean of the sampling distribution is 0.35. Okay, so that's saying the average of all of the p hats when I took samples of 1,500 first-year college students is 35%. What is the standard deviation of this specific curve? The standard deviation of this specific curve, or the standard deviation of the p hat, is 0.35, which is our successes, times 0.65, which is our failures, divided by our sample size, which is 1,500, take the square root. You must show this work plugged into this formula, which gives me 0.0123. Now notice this right here. This is telling me I have an approximately normal curve with a mean of 0.35 and a standard deviation of 0.0123, okay? All right, so what's the next step? Okay, so I have the mean and standard deviation. The next step is to say, okay, what probability am I actually finding? I'm finding the probability that p hat is between 0.33 and 0.37, Okay, well, how do I find the probability that p hat is between 0.33 and 0.37? We have a normal curve. Since we have a normal curve, we can use z-scores. We have a normal curve, we have the mean, we have the standard deviation, so I can use z-scores because I can find the area, okay, under a normal curve using z-scores. So remember, your z-scores are the sample minus the population divided by the standard deviation. So here's my z-score of 0.33, negative 1.63, which is right down here. Okay, then the next one is 0.37, sample minus population 0.35 divided by the standard deviation that I found up here is 1.63, so that's right here. Now you want to state, okay, now that I have it standardized, because on a normal curve I can standardize it, find my z-scores, now state the probability specifically of what you're looking for using z-scores. I want to find the probability that z is between negative 1.63 and 1.63, okay, between those two. All right, now you can do all of this on your calculator. So this is the same thing, normal CDF, negative 1.63 lower bound, 1.63 upper bound, and then your area, which is 0.8968, you can also use your table. Okay, so 89.68%. Okay, all the work shown on this slide is necessary. The work for the mean, okay, show what this is. The mean of p hat, you have to show those symbols. The probability statements, okay, so this probability statement right here with the p hat, specifically what proportions am I looking for, the work for the z-scores, and your probability statement using your z-scores. Do not just give me calculator speak. Do not just write normal CDF, negative 1.63, 1.63 is 89.68. You're not quite done yet, so you've done all these calculations. So state, what are we looking for? Plan, those are your assumptions, conditions, simple random sample, approximately normal, independent, do, okay, and there's all my calculations, and conclude. So I got a probability, so I need to make some sort of conclusion about it. All right, so what is my conclusion? So 89.68% of all simple random samples of size 1500 will give a result within 2 percentage points about the proportion of students that attend college within 50 miles of home. Okay, because this whole thing, because my curve was a sampling distribution of proportions, all right, and each of those proportions were samples of size 1500, all right, 89.68% of the simple random samples of size 1500, because that was for my sampling distribution, okay, will give a result, and then that's just from what the question was asking you. What happens if I get a small probability or a large probability as part of my final answer? So in the last step, what's it mean if I get a high probability of the event occurring? What about a low probability? So when there's a high probability, then it probably happened by chance alone, and what I'm looking at is actually not statistically significant. If I have a high probability, it's normal, it happens all the time. So in that last question, we had a high probability, so that was pretty normal, happens all the time, so that's not really statistically significant. That's just part of, you know, the normal process. But if I get a low probability, if there's a low probability, okay, then it did happen, not happen by chance alone. This means it's significant. If it's a low probability, it's really not normal. So think if something is low, not normal. It didn't happen by chance, and something is different than what we think. And we're going to be going into this in later sections, but just sort of get an idea of what those high and those low probabilities look like. All right, so why don't you try this one on your own? Take a minute and read it, okay, using the state, plan, do, conclude. So state, what are you doing? Plan, making sure you're showing it's a simple random sample. In context, making sure that you're showing it's independent, population's 10 times the sample size. Approximately normal, so that's your NP greater than 10, NQ greater than 10, showing your numbers plugged in. Then your do, what we went over, and then your conclusion. So take a minute, go ahead and pause the slide, try this question. It's going to take a few minutes, and then go on to the next slide when you're ready to go over the answer. Okay, so how did you know that you were doing a sampling distribution for this? Okay, take a look specifically at the question. What's the probability that an SRS of size 125 will give a result within 7 percentage points of the true value? You know that you're doing a sampling distribution because we're talking about the probability of a simple random sample of size 125. Okay, we're not just finding the probability that any given student is going to be within 7% of the true value, but if I take a sample, what's the probability that the sample will give a result within 7 percentage points of the true value? You should have used your state, plan, do, conclude method. All right, so 1, state. We want to find the probability that the percentage of middle school students who plan to attend a four-year college or university falls between 73 and 87%. Essentially, that's what we're doing. We're just restating the question, okay? Step number 2 is it has to be a simple random sample. Why? For inference. In order to make any conclusions about the population, it has to be a simple random sample of 125 students, okay? Let's prove it's approximately normal. NP, so 125 times 0.8, so our number of students times our successes is 100. NQ, our number of successes times our failures, 125 times 0.2 is 25. Those are both greater than 10. Therefore, it's approximately normal. Make sure you show the work and state it's approximately normal. There's no point in showing this work if you don't state approximately normal. Why did you do that? You showed that it was normal, okay? And then the last one, we can assume that there are more than 10 times 125 or 1,250 middle school students. Therefore, it's independent. So make sure that's in context. Don't just write 10 times 125. There's more than 10 times 125, 1,250 what? What are they? They're specifically middle school students, and you have to state, therefore, it's independent. So you did this work. Why? It's independent. I need it to be independent for the standard deviation. Okay, do. So we know we're talking about a sampling distribution because we're looking at a sample of 125 students. So what's the mean and the standard deviation? So the mean of p hat is equal to p, which is 0.8. You can just write mean of p hat as 0.8. Standard deviation of p hat, or my sampling distribution, is successes 0.8 times 0.2 divided by my sample size, square root 0.036. Therefore, it's approximately normally distributed with a mean of 0.8 and a standard deviation of 0.036. Okay, step 6. Step 6 is showing, okay, well, what proportion am I finding? I want my proportion to be between 0.73 and 0.87. All right, we want to know what proportion of students plan to attend a four-year college between 73% and 87%. Okay, so find those z-scores. Normal curve requires z-scores. Show the work for the z-scores. Label them, z equals, and then make sure you state what probability you're finding from your normal curve using z-scores. So I'm finding the probability that z is between negative 1.94 and 1.94, showing that probability. So that's saying that 94.76 of all simple random samples of size 125 will give a sample proportion within 7 percentage points of the true proportion of middle school students who are planning to attend a four-year college. Make sure you have all 7 steps shown exactly as listed. If not, you won't get credit. Okay, so this is a 7-step process. We learned that when we want information about the population proportion P, we have to take a simple random sample, use a sample proportion to estimate the unknown parameter. The sampling distribution of your population or sampling distribution of your sample p hat describes how the statistic varies in all possible samples. The mean of the sampling distribution of p hat is equal to the population proportion p. That is, p hat is an unbiased estimator of p. The standard deviation of the sampling distribution of p hat is your successes times your failures divided by your sample size, making sure that you write standard deviation p hat. The formula can be used only if the population is at least 10 times the sample size. That's your independent condition. The standard deviation of p hat gets smaller as the sample size gets larger. Okay, not as taking more samples of p hat, as the sample size within the p hat gets larger. So when the sample size is larger, the sampling distribution of p hat is close to a normal distribution, and the standard with a mean p and standard deviation of the following. In practice, the normal approximation can only be used when NP are greater than 10 and NQ are greater than 10.